Last time in phase equilibria, we left off with a Joule-Thomson valve for which we did a material balance, which wasn't really all that interesting, but we did a mole balance to find that N1 is equal to N2, rather negative N2 is equal to N1. And I said that if you knew what N1, T1, and P1 were, and what P2 is, you could calculate what T2 is. So by the energy balance, we also learned that H1 is equal to H2. And because the molar flow rates are the same, we simplified that into H hat or H under bar. Let me write the whole thing. H1 is equal to H2 hat or H1 under bar is equal to H2 under bar. At the very end of last time, I said that if you knew what the temperature and pressure were, so we know what T1 and P1 are, I'm going to go ahead and give those some numbers just to make the example clearer. So I'm going to say that P1 is 10 megapascals, T1 I'm going to say is 500 degrees C, and P2 is equal to 1.4 megapascals. N1 doesn't really matter what it is. We'll just go with our usual 100 kilogram moles per minute. All right, and how would you calculate what H1 is and then therefore what H2 is and therefore what T2 is? So at the very end, I said that H under bar or H hat is equal to H as a function of temperature and pressure. Now, how can I say that? How do I know that enthalpy is a function of temperature and pressure? How do I know it's not a function of something else? And if it is a function of something else, how do I know it's not a function of 3 things or 4 things? So let's take one question at a time. How do I know that H is a function of 2 variables? Recall the concept of Gibbs phase rule. And Gibbs phase rule tells me the number of intensive variables I must specify in order to specify the system. So by Gibbs phase rule, it says that the degrees of freedom is equal to 2 plus C minus pi plus R. So remember, components is C. These are the number of chemicals or number of species you have in your system. And pi is the number of phases. In most phase equilibria problems, you'll have at least 2 or more than 1 phase at least. But here we have 1 component, 1 phase. So he said it's a gas that's flowing through here. There is no chemical reaction. So my Gibbs phase rule in this case simplifies to 2 plus 1 minus 1 plus 0. That is equal to 2. So that tells us that I have to specify 2 intensive variables to specify the system. So this implies that if I specify 2 intensive thermodynamic properties, 2 intensive thermodynamic properties, then all other intensive thermodynamic properties are specified as well. Then all, still getting used to writing with this tablet, then all other intensive thermodynamic properties are therefore specified as well. So what does this tell me? It tells me that as long as I have 2 things, that's all I need. So therefore, I don't have to write H as a function of T and P. I could write H as a function of V and S if I wanted to. So why do I choose T and P? And it goes back to the concept of what do I know about the system? I wouldn't want to express enthalpy as a function of V hat and S because I don't know what V hat and S are. Those are properties that are more difficult to measure. In contrast, I have thermometers, I have thermocouples, and I have pressure sensors or pressure gauges. So typically, T and P are the properties that you will know in any thermodynamic system. When you're out in the field, for example, you will know the T and P of most process streams. That tells you that H as a function of T and P is going to get you to calculating enthalpy where you need to be. All right, so what is this function by which enthalpy depends on temperature and pressure? That is a question that is a little bit trickier to answer. And this is something that we'll get to in the next couple of weeks. But for now, let's just take an example. Depending on what the system is, what the gas is, that'll depend on what your function of T and P are. So suppose I had water. Suppose the gas is water vapor, and water in its gas form at high T and P is steam. How would I figure out what H as a function of T and P is? Well, water is arguably one of the most common chemicals, and because water is so commonly used, if I wanted to know what the enthalpy at a certain T and P were, I would have to look at the steam tables. And just as a lesson, anytime you have a steam table or any type of experimental data available, you always want to use that. So steam tables comes from experimental data. And therefore it is superior to anything else. You wouldn't want to use the ideal gas law or any other equations of state. The steam table is always the best. All right, so how do I use the steam table? So I would have to go to Appendix A3 in Sandler. Appendix A and 1, 2, 3. And I would want to look up H1 and the conditions there. The T is 500 C and 10 megapascals. I'm going to pause the video for a second because I need to go look this up. And for those of you who have the 4th edition, I am on page 923. And I find that at 10 megapascals and 500 degrees C, my enthalpy, specific enthalpy of water. So this is important. Sandler gives you H hats in the back here, not H underbar. So this is per kilogram. It's 3373. Oops, 3373.7 kilojoules per kilogram. All right, and therefore I know that H2 hat at some unknown T2 and 1.4 megapascals is also equal to 3373.7 kilojoules per kilogram by the energy balance. The energy balance says H1 hat is equal to H2 hat. So the trick here is now finding out what this T2 is. So because I know what the pressure is, this way, the steam table is arrayed, if you know what the pressure is, you just go and you find where the pressure is. So 1.4 megapascals is on the previous page, all the way at the top right, and I have 1.4 megapascals there. But I run into a problem. Because I don't know the temperature, I can't simply look up what the H is. So if I look carefully, I see that 3373.7 will fall somewhere in between two data points. So I have two options here. I have H hat for a T of 400 C and 1.4 megapascals is equal to 3257.5. So verify this again yourself, kilojoules per kilogram. And I have one other data point that says H hat of 500 C, 1.4 megapascals is equal to 3474.1 kilojoules per kilogram. So what do I do now? In cases like this, it's typically appropriate to interpolate. So if I assume that the data is exactly linear between these 2 points, that will give me an approximation. Now this ruins some of the accuracy of the steam tables, of course, because now you're approximating a little bit. So if you don't have the exact data, I guess you wouldn't say that the steam table is always the best, because sometimes you have to interpolate nonlinear data and pretend that it's linear. But the approximations that it gives you won't be too bad. So remember how to do interpolations. And because you may frequently have to do interpolations in this class, it may be worth it to code yourself an interpolation calculator using Microsoft Excel. So this will be the first Excel tutorial that I give you. So I want to stop my share, and I want to instead share Microsoft Excel. All right, and I'll show you how to make yourself a little interpolation calculator. You want to input the data that you have. So I'm going to say H and T, and for an enthalpy, I guess in the first column will be your dependent variable. So H is dependent on the value of T. So I have data for 400C and 500C, and this middle value is the one that I want. So I like to color code my stuff in Excel. So I'm going to make the outlet cell is going to be in green. And I don't like how it aligns stuff. I like to center things in Excel. That's just my personal preference. I'm going to take the data that the steam table gives me, so 3257.5 kilojoules per kilogram and 3474.1 kilojoules per kilogram. All right, so I need a convention. I'm going to color this in, let's say, orange to tell me that this is data that I get. And I'm going to say that the blue one is going to be the point that I want. So the point that I want has to be in between, which is why I arrayed it like this. The temperature that I want to calculate is 3373.7. Now, how do I go about calculating? Remember the equation for interpolation. All right, I just pause briefly so that I can get the interpolation formula. Remember, the way you derive this is that you say that the slope of the line that connects the two known data points must be equal to the slope of the line that connects the unknown data point to the known data point. So it's rise over run. I'm not being very careful in terms of which one I call the dependent variable. I think when I solve for y here, I probably should have solved for x, but because it's a line, it really doesn't matter which one you use. So I could just as easily plot t as a function of h for the purposes of interpolation. But what I really want here is this solution for y, and this is the formula that is going to go inside this green cell. So y is equal to, so equals y1, so that's the temperature plus, and in parentheses, I'm going to have the temperature difference, so y2 minus y1 times x minus x1. So x is a3 minus x1, all divided by the whole interval a4 minus a2. And I'm not copying this formula, so I don't need any dollar signs. And if I click enter, it's going to give me that the temperature is 454 degrees if I round. So you can use this formula for any interpolation that you have to do. All you have to remember is to replace the orange cells with data points that you know, replace the blue cell with the data point that you want to find out about, and then this calculator will automatically calculate what your temperature is. So this tells us that T2 in the Joule-Thomson example is less than T1, which perhaps makes sense because, again, pressure and temperature go together. So if pressure decreases, temperature will also decrease. But as we'll see coming up, that's actually not always the case. So in the next video, I'm going to show you how you would calculate this using Unisim software.